Okay, we are moving into chapter 7. For chapter 7, for a lot of students, this is one of the most challenging chapters because it's very abstract in the way you have to think and understand the concepts. Not so much today, but as we get into sections 7.2 and 7.3, they're really at the foundation for all of inferential statistics, but they do become a little bit challenging here. So let's lay the foundation here today. So we're talking about what's referred to as a sampling distribution. When we're talking about a sampling distribution, the whole concept in statistics is it's very difficult to collect data on the entire population. So we take a sample, a subset of the population. Hopefully, we're making sure that that sample is representative. And then we use or make an inference to come up with some idea about the entire population. Now, along those lines, there's some important things that we need to go vocabulary wise. First of all, we have this idea of a parameter. A parameter is a number that describes some characteristic of the entire population. So you want to be able to think of these two things, parameter P goes with P population. A statistic is a number that describes some characteristic of a sample. So statistic, sample, S and S, okay? So think of parameter, population, statistic, sample. So we've got three really important parameters and statistics that we care about. The first of which is your sample mean and your population mean. And notation is crucial. So we have X bar, which is our sample mean, and mu, which is our population mean. So for example, maybe I want to think about the average GPA of South students. If I ask every single student at South their GPA and find the average, I'm taking mu, the population mean. Mu looks like almost like a mix between the letter M and U. Say I decide, okay, that's too difficult. I'm only going to randomly select 100 students and find their average GPA. Then I've taken an X bar, okay? I've taken a sample mean. You've got P hat, which really looks like P with a little caret on top. We call that P hat. That's a sample proportion. Then you've got P, just the capital letter P, which is the population proportion. So proportions are percentages or the amount out of the whole. So for example, I want to know what percentage of South students believe in ghosts. So my population is all South students. I ask every single South student, do you believe in ghosts? And I find the percentage. I've found the P, the population proportion. I take a random sample of 50 kids and I say, do you believe in ghosts? And I find that percentage. That's a P hat, okay? So P hat is your sample proportion or your sample percentage. P is what's true for the entire population. And it depends what your population is. Your population could be all adults in the US, could be all seniors at South. It could be all people in Middletown. Whatever it might be, okay, that's your population. And then finally, you have S or SX, which is your sample standard deviation. And then you have what looks like an O with a little tail. That's the Greek letter lowercase sigma. That represents the population standard deviation. So on my left-hand side, all of these are all statistics. We use statistics to estimate your parameter values. It's very rare that we'll know these values here. So we use these guys and we find these, and we use these to estimate what these are actually at. The following two examples we'll do in class. Let's look here. Identify the following, write a P if the variable is a parameter and S if it's a statistic. So if we go through the list, N, capital N, represents your population size. That's a parameter. Lowercase n is your sample size. That's a statistic. X bar is the sample mean, statistic. Mu is the population mean, parameter. S is your sample standard deviation. That's a statistic. Lowercase sigma, population standard deviation. That's a parameter. And then finally, P is the population proportion, so that's a parameter, and P hat is the sample proportion, which is a statistic. So make sure you're clear on the notation here. Now, within all of this, okay, how can X bar be an accurate estimate of mu? After all, different random samples would produce different values of X bar. So even if we all say, I want to estimate, again, I want to estimate the GPA of South students, and I have each of you randomly select using the same technique 50 students at South or 100 students at South, we're all not going to get the same sample mean, okay? Even if we use the same exact sampling technique. That basic fact is what we refer to as sampling variability. The value of the statistic, in this case our sample means, is going to vary in repeated samples. So to make sense of sampling variability, we ask, what if we took many samples? So now everyone's going in the population and taking many different samples. That's what's referred to, again, as sampling variability. Individual observations will vary, as will samples, and we're trying to estimate the variability to know how close we are to the true population parameter. We'll look at the next example down in class. So with that, we have this idea and this concept of a sampling distribution. So a sampling distribution means if we took every one of the possible samples of size n from a population and calculated the sample proportion or the sample mean for each of those and graphed those values, we'd have a sampling distribution. So the formal definition of a sampling distribution of a statistic is the distribution of values taken by the statistic in all possible samples of the same size from the same population. In essence, your sampling distribution is a collection of every single possible X bar or P hat that you would get. So say we went out and we're trying to estimate the GPA of a South student, and I had everybody go out an infinite amount of times and record your X bar value, and we graph those. That's what a sampling distribution is. It's really a graph of every possible X bar or P hat. Okay, that's shown in the example right here. Here's our population distribution. We've got 200 chips. 100 are blue and 100 are red. We're taking samples of size 20. So you might get a sample where 12 are blue and 8 are red. Or you might get 9 blue and 11 red. Or you might get 7 blue and 13 are red. These are all individual P hat values. We know that P, the actual proportion that are red, is split evenly 50-50. This right here is your sampling distribution. It is a graph that is plotting every single possible P hat of size 20 that you can get from this population here. Okay? And notice the shape of this graph. This doesn't happen by coincidence. Notice that the shape is pretty normally distributed, centered at what the population distribution is. But you might get samples as low as 15% red to as high as 80% red as a part of your samples. So again, what is a sampling distribution? It illustrates or graphs all the possible values of a sample statistic and shows how often they occur. We need to know what counts as usual and unusual. We can determine that by looking at the graph. So in simplest terms, you want to think of a sampling distribution as the graph of all possible either X bars or P hats or S's. Let's talk about the difference between each of these concepts here. The distribution of the population, the distribution of the sample, and the sampling distribution. The distribution of the population refers to mu or sigma or p. It's referring to your entire population. It displays every value of the actual population. So if we want to look at the data for every student at South and the number of pets they own, and I record that, say, in a dot plot, that would be an example of the population. Here in this one, when we're dealing with the proportion, this is your population distribution right here. 50% blue, 50% red, or 100 blue chips and 100 red chips. The distribution of the sample displays the values observed during a single sample. So say we're asking how many pets they own, and I ask 30 students, that would show the sample of my 30 students, your X bar, your S, your P hat, for your lowercase n. In our example up here, these are my individual sample distributions, where I got 12 blue and 8 red, and so on and so forth here. This is my distribution of my single sample. Finally, the sampling distribution displays all possible values of the sample statistic from the same size and population. That's our collection of all of our little X bars or our P hats. So this right here is our sampling distribution. We're now on a graph. I'm plotting each of my individual P hats or X bars that I get. Very, very important concept for you to understand. So next thing that we want to talk about is the difference between a biased estimator versus an unbiased estimator. In the chips example, we collected many samples of size 20 and calculated the sample proportion of red chips. How well does the sample proportion estimate the true proportion of red chips? If we take a look at our graph, which is again shown right here, notice that the center is very close to 0.5, which is what the actual true proportion is. So our sample or our estimator did a very good job of estimating the actual value because it's centered at what the true proportion is. So a statistic used to estimate a parameter is an unbiased estimator if the mean of the sampling distribution is equal to the true value of the parameter being estimated. Notice that we're centered at around what the actual value of P is. So because we're centered around the true population parameter, and it doesn't have to be exactly perfect, then we have an unbiased estimator. If our graph was centered at around 0.6 or at around 0.3, and we know the true value is 0.5, that would mean our estimator is biased. It is consistently too high or too low. It systematically over or underestimates the actual value. When we're talking about spread, we're looking for low variability. So we'd rather have all of these values in here be clustered closely towards the center. Low variability is better. So to get a trustworthy estimate of an unknown population parameter, start by using a statistic that's an unbiased estimator. That ensures that you won't tend to over or underestimate the value. Unfortunately, using an unbiased estimator, there's no guarantee that the value of the statistic will be close to the actual parameter value. So one thing that we can do to help us reduce the variability is to increase the sample size here. You've got two examples taken in the exact same way. One, we're taking a sample of size 100, and one, we're taking a sample of size 1000. I know the graphs didn't show up that well on this particular copy, but you can see here, if you look closely at the graph, this one, my samples vary anywhere from 0.22 to 0.52. So there's a range of 0.3. Here, my samples vary from 0.31 to 0.43. So the range is only 0.12. So as we increase the sample size here from 100 to 1000, we've reduced the variability in our p hats, or in a different case in our x bars. So increasing sample size is going to decrease the variability of your individual samples. Larger samples have a clear advantage over smaller samples. They are much more likely to produce an estimate close to the value of the parameter. There are general rules for describing the spread of the sampling distribution of a statistic. It decreases as the sample size increases. One important and surprising fact is the variability of statistic in repeated sampling does not depend much on the size of the population. So it doesn't matter how big of a population you're taking it from, it matters how large your sample size is, and that's a crucial thing there. So the variability of statistic is described by the spread of the sampling distribution. This spread is determined mainly by the size of the sample. Larger samples give smaller spread. The spread of the sampling distribution does not depend much on the size of the population, as long as the population is at least 10 times larger than the sample. So if we want to reduce the variability of a statistic, we're going to increase the sample size. Obviously, another way that we can reduce variability is to improve the study design, aka a stratified sample. What effect does the population size have on the variability of the statistic? Virtually none. Population size has very little impact on sampling variability as long as your sample size is less than 10% of the population size. Last thing for today, kind of bringing it all together with bias, variability, and shape. So if we want to think of the difference between bias and variability as well as accuracy versus precision, we can think of our examples of our targets right in here. So bias means that our aim is off and we consistently miss the bullseye in the same direction. Our sample values do not center on the population value. High variability means shots are widely scattered on the target, and repeated samples do not give very similar results. So we want to think of accuracy as unbiased, centered at the true population parameter, while precise is low variability, it's consistent and has tight grouping. So obviously in example A of our bullseye, it's clearly biased because we're not close to the center here and it's in the same systematic direction, but there's low variability. They're all tightly clustered together. So this is high bias, low variability. Here we're centered close to the mean, so there's low bias. We're right around the target, but there's high variability going in all of the different directions. In C, with our target here, we're both not centered around the target at all, and we're consistently in the same direction, and there's high variability. So there's high bias because we're not centered around the target and we're in the same direction every time, and there's high variability because we're really spread out. Finally, this is our ideal representation here, where we have no bias, we're centered right around the actual target, and we have low variability. They're all clustered together. We'll talk more about this in class. See you then.